In this class I am going to talk about Newton's experimental law of restitution. I'm going to go through one example. I'm going to introduce the law. First I want to just look at a quick graphic here. So what I want to do is I want to think about some ball here, little red ball being dropped onto some floor, and what happens to it. I'm going to look at it only just for 2 or 3 bounces. I'm not going to look at it through its whole path. So if I just play the animation here, notice where it's dropping from. I might just put my arrow there at the height from which it's dropping. Play my animation. So it's dropped from this height up here. It drops. It doesn't reach the same height again, and then it goes a little lower each time. And I'm just going to look at those 3 bounces. Obviously it doesn't just stop dead on the 4th one. So I'm just going to look what happens here. So again, let me roll back to the start. So it's launched from up here, or dropped I should say, then it goes to here, and then it goes to here. And what Newton observed was that each time it rebounded, I'm just going to actually play that over and over again, so let me just play that over and over again. So each time it bounces, it's losing a little bit of speed. We looked in our last section about collisions and impacts, and things can lose a little bit of energy when they collide with things. The energy goes elsewhere. It doesn't just disappear. It goes into something else. But here, and again, I'm only looking at 1, 2 bounces really on what's happening. So on that first bounce it loses a little bit of speed. On the second bounce it loses a little bit of speed. And that's why it's going a little less high each time. It's starting from quite high up. It won't go as high up because it's not going as fast on its rebound as it was on its impact. And each time it rebounds it's losing a little bit of speed. And Newton formulated this into something called his experimental law of restitution. Okay? And restitution really means bounciness. So what he said is that really if you took the rebound speed and divide it by the impact speed, it's always in and around the same thing. And he called that E, the coefficient of restitution. So E is the coefficient of restitution. Another way of saying that is that the final velocity is equal to negative E times the initial velocity. Why negative? Because it's in the opposite direction. Obviously, when it strikes the floor, it's changing direction, so introducing that negative sign, and then E just multiplying by that impact speed to give me my final speed. Okay, it's not the same as Euler's E that you see in mathematics, which is about 2.7. It's not a fixed constant. Bounciness depends on, the materials involved. Different materials will have different restitution, different bounciness. Okay, so restitution just think of for the moment as bounciness. So let's look at an example here. It says a ball of mass 100 grams strikes a wall at 20 meters per second and rebounds at 18 meters per second, all in the horizontal. And find the impulse imparted to the ball and the loss in kinetic energy. So how can a ball strike a wall in the horizontal? So if I just think about, some wall like so, how can a ball strike it horizontally? Like a ball, if you throw a ball, it doesn't move in that direction. Well, what we mean is, again, like we were talking about our last section, we're talking about immediately before impact and immediately afterwards. If you throw a ball, in fact, its path will follow a kind of a parabola. But at that moment of impact, that is just turning, it's just horizontal at that moment. Okay, so we're talking about immediately before, it strikes immediately before, and then immediately afterwards. We're talking about an instantaneous change from 20 to 18. All in the horizontal. We want to find E. Okay? Well, remember, the easiest way to, I suppose, to remember this is just to remember E is just the rebound speed divided by the impact speed. So E is going to be 18 divided by the impact speed, which is 20, which is 9 over 10, or 0.9, or 90%. Any of those things are fine. E is always a number between 0 and 1. It can't be 1. If E was 1, what you would have is perpetual motion. You'd have something, you could drop an object on the ground. If E was 1 here, we'd just keep going up and down to the same height forever and ever. But that can't happen, you know. If E was bigger than 1, well, then it would be gaining height each time it bounced, and gaining speed, which would be, you know, a problem, I suppose. It kept gaining speed, it was getting faster and faster. You could drop something from just an inch above the ground, it would gain speed, eventually it would be flying around the room like a bullet, and eventually much faster than that, faster than anything you could imagine. So, you know, E is always between 0 and 1. In this case, it's 0.9. So if you accidentally put impact over rebound, you find 10 over 9, you think, well, it can't be that. It can't be bigger than 1. I've made a mistake. Okay? Find the impulse imparted to the ball. Well, impulse is defined, I'm hoping you can remember from our last section, as the change in momentum, which is mass times v minus u, mv minus mu, final momentum minus initial momentum. M is 100 grams. We're dealing with kilograms, so we're going to call that 0.1 times v, the final velocity. Now, final velocity here, we're dealing with velocities when we're dealing with momentum. So I'm going to have to think about, you know, positive and negative. So maybe I'll call this a right positive system, which means its impact speed will be positive and its rebound speed will be negative. So its final velocity in that case would be negative 18, and then subtract its initial velocity, which would be positive 20, which would be 0.1 times negative 38, which would be negative 3.8. On my units for impulse, we're talking about Newton seconds. What's the loss in kinetic energy? So there's 1, find E, 2, find the impulse. What's the loss in kinetic energy? Well, change in kinetic energy is just the final kinetic energy. So EK final minus the initial kinetic energy. If it's a loss, it's going to be negative. Which is a half mv squared minus a half mu squared, or a half m times v squared minus u squared. In this case, we're talking about speeds. Energy, we're dealing with speeds. Momentum, we're dealing with velocities. So m, well, that's 0.1 over 2 times its final speed squared. It was traveling at 18 squared at the end, minus initial speed squared, that's 20 squared. Okay, and a bit of calculation to do in there. So 0.1 over 2, that's 0.05, 20 squared, 400, 18 squared is something that I'm going to use a calculator for. So 18 squared is 324. So we're getting 0.1 over 2, which is 0.05 times 18 squared, 324, minus 20 squared, which is 400. Okay, just plug it all into your calculator. And what I'm getting is negative 3.8. On my units here, it's joules, because we're dealing with energy. Okay? So that's Newton's experimental law of restitution for an object striking a plane. Okay? If it's two objects striking, it becomes a little bit more complicated, but more or less the same thing. Okay, we deal with what we call relative velocities at that stage. Okay, so E is the rebound speed divided by the impact speed if I'm taking speeds. The impulse is the change momentum of an object, and to find the kinetic energy, that's negative 3.8. That means it's a loss. Actually, the last one says find a loss in kinetic energy. Negative is telling me it's a loss, so I'm going to say therefore the loss in kinetic energy is equal to 3.8 joules. Okay, so get used to that, practice a few of those. We're in 7A in our textbooks.